All right, this is a great chapter here. We're going to talk about something that we always have been ignoring kind of in the past, right? It's called chemical equilibrium. Any ideas what that might mean?
Equilibrium. We've talked about equilibrium before.
We have. We've talked a little bit about it. In the past, we talked about equilibrium when we were talking about weak acids. Do you remember that?
Yeah, because in a weak acid, like, what's an example of a weak acid?
Well, let's just use a generic HA, right? Acid starts with the H, A.
Okay, yeah. A weak acid, its dissociation has double arrows. So that's equilibrium, right?
Very good. That's a good memory. Double arrows like that. And what does that mean when I write something like that with double arrows?
Oh, that means that HA react to form those products, but then those products come back together to form the reactants.
Very good. That's right. And in reality, almost all reactions are occurring in equilibrium. And in biological systems, again, more than almost all, essentially all reactions are occurring with an equilibrium, where the products can react again to form reactants. So we have to have a way to talk about equilibrium and understand it and see how it impacts the natural world, because it's a huge impact. And again, these are eternal principles that you have to kind of be aware of here. All right, we call it dynamic equilibrium because the reaction, the forward reaction, here's our reactants here, here's our products here, the forward reaction never stops occurring, and the reverse reaction also never stops occurring. Now, if we were to plot concentrations of reactant and product over time, start off with a lot of reactant, no product. The reactant starts to form into products, so the reactant's concentration goes down, the product's concentration goes up, and you would come to a point where the reactant's concentration no longer changes, all right? And the product's concentration no longer changes. And we call this equilibrium, equilibrium. Now, it doesn't mean, again, that none of my reactant is forming products or that none of my products are reacting together to form reactants. It just means that the rate of these two reactions is such that the relative concentration of reactants and products is not changing, okay? So, again, very important to recognize. Now, notice here that the rate, the slope, at which the concentration is changing over time, right? That slope is actually changing again, right? So this reaction changes, how fast the reaction proceeds changes over time. Same with this reaction here, right? The slope changes over time, showing that these reactions are dependent on their concentrations of each other. And that's from last chapter, right? Okay, so whether we start with all reactants or all products, we're going to reach equilibrium.
When heated in a closed system, calcium carbonate will decompose to form calcium oxide and carbon dioxide. As the amounts of calcium oxide and carbon dioxide increase, a reverse reaction occurs and calcium carbonate is resynthesized. When the decomposition rate of calcium carbonate equals the synthesizing rate of calcium oxide and carbon dioxide, the system is said to be at dynamic equilibrium. Now suppose most of the carbon dioxide is removed from the system and the system is resealed. The rate of synthesis of calcium carbonate from calcium oxide and carbon dioxide will slow down and almost stop.
Okay, did you hear that? The rate of synthesis of calcium carbonate from calcium oxide and calcium dioxide, the rate at which the reaction will go towards reactants, will stop because we just let go of the carbon dioxide. And if there is some, it's very little, and the calcium oxide needs to find the carbon dioxide to form calcium carbonate, right? So we let go of our material. This is a product, but if you look at it from the bottom arrow's perspective, it's not a product, is it? What is it?
Oh, it's like a reactant.
That's right. It's like a reactant for this bottom arrow. And this is the product for the bottom arrow. So if we let go of this reactant and there's hardly any of it left, then the rate at which the bottom arrow can form this product over here is going to be very slow because there's just not much of it, hard to find. The collisions have to occur appropriately, right? Okay, so if we let it out, then the reverse reaction will not occur until what?
I don't know what.
Well, he'll tell us.
However, the decomposition of calcium carbonate to form more calcium oxide and carbon dioxide will continue. As the level of carbon dioxide increases, the reverse synthesis of calcium carbonate will again begin. Eventually, the decomposition reaction rate will equal the synthesis reaction rate, and equilibrium will be reestablished. But because some of the reactants were removed, the equilibrium has shifted.
All right. So what we're trying to emphasize here is this term dynamic equilibrium to help you recognize that products and reactants continue to react to form each other, whether you're talking about these as reactants and these are the products, or these are the reactants and these are the products. However, the rate at which it occurs will be such that when you reach equilibrium, their actual concentrations of all of these will not be changing. All right, good. So we want to have a way to express the condition of the equilibrium for a given chemical reaction. So let's say I have this chemical reaction here. This is A plus B forming C and D. I put little a's, little b, little c, little d as their coefficients here. But this is essentially A plus B coming together to form C plus D. We have an equilibrium here. All right? And we want to have a way for me to express to you, or one chemist to another, what is the status of this equilibrium. All right? Now we could have a scenario where, for example, A plus B, I'm going to rewrite it here, C plus D in equilibrium. It could be that the way that this is written, the kind of chemical reaction it is, maybe it's all occurring in a balloon and it's all of these are gaseous, let's say, just to simplify our scenario. It could be that A and B react very fast and form C and D. But C and D, it takes a lot of time and energy for them to react, and therefore they don't form A and B as quickly. And if that's the case, in equilibrium, when you've reached equilibrium, A and B, as soon as they form, they react and form C and D really fast. And so most of what you have in the balloon is going to be C and D, with very small amounts of A and B. Because as soon as the A and B form, it forms C and D. But the C and D, on the other hand, it takes a little bit of energy. But this equilibrium, I mean, as it's drawn right here, it might also be the opposite, that A and B react very slowly and C and D react very quickly. And therefore, A and B are going to be what predominate here, and C and D are going to be in small concentration. Well, which one is it? Is it this or is it this? You can't tell by looking at the equation. All we see here in the equation is that there are reactants and products as it's written, but really we see, because we see it's equilibrium, these could be reactants and these could be products. So we don't know where the equilibrium is at. Is it mostly A and B, sorry, mostly C and D, mostly A and B? It could be that it's exactly the same relative concentrations, that the reaction at which A and B occurs, the rate is the same as which C and D occurs. Therefore, everything's the same in terms of, everything's fixed in terms of their concentration, but at equilibrium you have a significant amount of everything. So we want to have a way, a number, that when we write the number, it will tell us about the equilibrium just by looking at that number. And this is the way that we've decided as chemists to get a number that will tell us about the equilibrium. And that number is called the mass action expression. And we get it by taking the concentration of our products, raising them to the coefficients on those products, dividing it by the concentration of reactants, and raising those to their coefficients as well. All right? So if at equilibrium, the concentration of A, B, C, and D are all the same, let's say 1, 1, 1, 1, 1, and the coefficients are all the same, 1, 1, 1, 1, everything here would be 1, 1 divided by 1, Q would be 1. So if I say Q equals 1, that means, and under the conditions that we have, the concentrations of these are relatively the same. If at equilibrium most of it is CD and there's very little AB, then these values, C and D, would be large and A and B would be small. If C and D are large and A and B are small, then what would Q be?
If C and D are large, then Q is going to be a big number.
That's right. So if Q is 1, that would be an indicator that all of these are relatively similar in concentration. If Q is something large, like 10,000, then that means that we're in a scenario where products predominate in our equilibrium. And vice versa, if I had a lot of reactant and very little products, then this would be a small number, this would be a very large number, and Q would equal something like 0.0001, very, very small number. So if I told you the Q for this reaction is 1, then that means that at equilibrium, all these concentrations are fairly similar. If Q is a very large number, that means that at equilibrium, you have mostly products. And if Q is a very small number, that means at equilibrium, you have mostly reactants. All right? So dynamic equilibrium will be reached when you have reactants and products that can react both ways. And we can express the current equilibrium condition with a Q value that is an expression, a mass action expression for a given chemical reaction. Good.